Penn Island, you need to change your name, exit, and re-enter.
I'm trying to.
Okay.
I was in with some friends the other day.
Okay. We'll be starting here in a couple minutes. If you want to go get yourself a drink, something to eat, feel free to do that. Penn Island, if you can't figure out, if you can't change your name, make sure you put your turn your camera on, and that would be alternatively okay. So camera on.
I changed this.
Okay.
Morning.
We'll be starting here in a few moments. If you want to go get yourself something to eat or drink, that's fine. Go to the restroom real quick. Danny, which Danny is this? Is this Tanel? Dan, which Dan is this? This Long?
Dan Long. Yeah, I typed in my name in the chat.
All right, that's fine. Okay, thanks.
There we go.
Jack Lauer, I need your whiteboard, so send those to me, and then I will let you re-enter. We'll get started here in a minute or so. Emily, I need you to send me your impulsive labs. I have your explosion whiteboard, but not your impulsive one. So if you can get that to me, please.
Hi, Brandon. This is Jen Hartley, and speaker from Deer.
Okay, I think we're going to go ahead and get started. So let me, okay, so let me share my screen with you. And get this out of the way. Okay, Canvas. All right, so today what we're doing is we're going to be whiteboarding the two labs that I asked you to do, the explosion lab and the impulsive lab. By the way, we're going to try to make this as much like it is class as possible. So what that means is, yes, I sent you a whole bunch of whiteboards, just like the lab response. I try to chunk it up to make it easier, because if you make it one big long Google draw, every time you type, it kind of makes you go back to the top, and it gets really annoying from your standpoint. And I didn't want you to be too annoyed with it, so that's why I chunked it down like that. But I don't expect you to be able to do all those problems. Don't think, well, like, oh, you had to get that whole thing done. No, I just wanted you to do just like in class, and that is have your graphical models ready, have your mathematical models ready, and have those whiteboards ready for just those graphs and the mathematical models. That's it. So not any different than normal. I just expect you to come to class prepared. So hold on a second while I'm checking here. Jack's. See, Jack, there isn't anything on here. Let's see. Yeah, that's the only one I see. Okay. All right. So that's kind of all I was really expecting from you. Just having those ready, prepared for class. We're probably not going to get much further than that, since we have two labs we're looking at, is the explosion, just the graphical mathematical models, and the impulsive lab with the graphical and mathematical models, and that's kind of it. All right, so I think I'm just gonna quickly kind of remind you what was happening in the explosion lab. Oh, I probably also ought to mention this too, since we're all kind of learning this, and I'm trying to learn how to manage this. I mean, I got like 200 emails the other day. Some students, and I think you just saw Jack there, some students were sending me an email for every one of the whiteboards. It would really be nice if you just simply make one Google folder to put all of those in, and then share that folder with me. That way it's one email, easier for you, easier for me, more organized that way. Also, you can work with other people on these whiteboards, just like in class. I don't have a problem with it, but you need to understand, from my vantage point, I need to be able to see that everybody's participating. And the only way I can see that is by looking at the history. So for instance, what you can do is everybody can get their own data, but you don't have to graph everybody's data. You can just have a discussion on the whiteboard, do a little chat. Hey, this is what I got. I got a linear model, whatever. Is that what you got? Yeah, whatever. And then pick one person's the whiteboard, but everybody can help that person. So maybe one person does the axes, labels them and numbers them, maybe and titles it. Maybe one person draws in the best fit line, the point protector, slope indicator. Maybe another person does the mathematical model. I don't really care how you divide it up, but realize that if it's one person that's putting all the stuff on there that's that I can look at in the history, I can't see that everybody is participating. So I mean, try to look at it from my vantage point. I totally understand that you guys could be talking behind, unbeknownst to me, with one another, and then one person's doing it as a secretarial thing, but I need some way of verifying that everybody's participating. So unless you can think of some other way, some people are, everybody's doing their own. That's fine. It seems a little burdensome for you, but if that works best, whatever. Okay. So I just kind of want to share that with you. It's not like I'm expecting you all to do your own independently. Trying to make it as much like classroom as possible. Okay, so first one we're looking at is the explosion lab, and what that was, you had these two cars that were kind of, you're triggering it somehow, and they're kind of exploding away from one another. And depending upon how much mass they had, how much inertia they had, they might have been going faster or slower than one another. Notice my hands are moving away from one another. That means one's moving in a certain direction, the one's moving in the opposite direction. So mathematically, that means there might be a negative sign involved. All right, so let's see what people had for this. So imagine this as me going around the room, excuse me, looking at all the graphical relationships. So this person here kind of shows kind of an inverse relationship. Keep in mind, I think it really would have been a negative inverse. So some students might go, well, Mr. Lempasti, why didn't you draw the axes kind of, you know, rotated around? I understand that, fair criticism, but I also didn't want to give you too much of a hint. I wanted you to be thinking about, hey, they're moving in opposite directions. How do we handle that? So you could have rotated the coordinate system here, or I think my solution would have been just simply to draw the axis up here and kind of ignore the other axis down there. Maybe somehow change it to white. Something like that. Oops, let me get rid of the line here. There. So something like that. And then I think what would happen is I'm going to show you what I would do to draw. There's lots of different drawing things. I know we're all learning this. I'm playing around too myself. I don't know, maybe something like this. Okay, and then linearizing this. Again, I think when you linearize this, it will give you a linear line, but I think it's going to be below the axis. So I think maybe this is how I would change it a little bit. Let's see if I can just copy and paste. And I think then it would have went like this. So, okay, so I think it would have been a negative inverse. Let's see what other people have. Again, I think it's going to be a negative inverse, but they have an inverse relationship. So what I'm pointing out here is that the speeds, we actually kind of, what you graphed here really was a ratio of the speeds over the masses. But since they're going in opposite direction, and I wanted you to graph a ratio of the velocities, it's really going to be a negative inverse. Seems a little subtle, but there you go. Negative inverse, same thing. I think it's negative inverse. Okay. So I think we're all kind of in agreement so far. Okay. Okay, so it looks like they squared the velocity, and I understand that it might be a little bit confusing, but probably when you looked at your graph, it actually was an inverse relationship. It just simply was below. So I don't think you really want to square the velocity. I don't think that'll help that one. Let me check my email real quick because I'm hearing, let's see. Daniel says he has something, so let's see if he has the explosion one. Huh, Daniel. Daniel's saying it's linear right off the bat. Okay, so he's kind of the odd man out there. So let me kind of go back to each of the individual ones. So now looking at the linear relationship, I think what we need to include in here would be a negative symbol or a negative sign. So it's a negative inverse. And so realize that when you divide by the ratio of mass over red over mass over blue, that would be the same as the following. So I'm going to add to this one here a little bit. This would be equal to then velocity of red divided by velocity of blue equals, now I can still have, I'll still have a negative here, but when you have a complex fraction, dividing by a fraction would be the same thing as multiplying by the reciprocal of that fraction. So it would be negative mass of blue over mass of red. So if you look at the fractions here, notice I have red over blue, and then on the other side I have blue over red because it was a negative inverse relationship. So any questions there anybody has? I think that's kind of what everybody is kind of showing, most people are showing, okay? I want to go a little bit further than this because dealing with these fractions is kind of a pain. So I'm going to multiply both sides by the mass of the red to simplify the right-hand side. And I'm going to multiply both sides by the velocity of the blue to simplify the left-hand side. That way I won't have any fractions. And so when I do that, I'm going to have mass of red times velocity of red equals, on the left-hand, or excuse me, on the right-hand side, I have negative mass of blue times velocity of blue. I can't spell, sorry. Okay, so I believe that would be our consensus mathematical model. Okay, at this time I need to give you a new definition, and that's for momentum. Momentum is kind of like inertia, but it's inertia in motion. So again, you had these objects that were exploding away from one another. One object, though, the more massive one was probably a little bit slower than the smaller one, the one that was least mass or had less mass. So therefore, we're looking at the inertia, but the inertia is kind of in motion. So momentum is kind of like inertia in motion. That's conceptually what I want you to think of. But really, the mathematical relationship I want you to have is momentum is equal to the product of mass times velocity. And I want to go a little bit further than this. And that is, I need to kind of give you the mathematical with variable equation. So the variable, the letter we use for momentum is actually a P. If I remember correctly, one of the first scientists to study this, I believe, was Newton. And he knows this relationship. Hey, this more massive one, it seems to be going slower than this smaller one is. And I think he labeled it with kind of the Latin name of that's similar to progress. So it's kind of the progress of an object. So momentum, we use the letter P. And that's going to be equal to m times v. This is a vector quantity. So I'm going to put an arrow above the v, because velocity, of course, is a vector. One was going in the positive direction, the other one's going in the other direction. So let's say it's negative, which means momentum is also a vector quantity. So for this, I want you to think about this. Again, these things were exploding away from one another. This momentum, like the momentum of the red or the momentum of blue, was that the initial momentum or was that the final momentum? So somebody say something.
Final.
Yeah, that was the final momentum. So I'm going to put a F here for both of these. In fact, the initial momentum, before it was even triggered when it was just sitting there, what was the initial momentum of either car?
0.
Is that 0? Any questions on that? So what I wanted to get from this is that I want you to see that their momentums are related. This new idea of momentum, which is inertia in motion, mass times velocity, they're related to one another, okay? Okay, any questions? So I think that's kind of all we're doing on the lab for this one. Now let's look at the impulsive lab. Let's see, here it is. So again, pretend this is, again, the lab. We're just looking at the whiteboards from everybody, trying to see what the relationship is. So I'm not really sure what we're saying the relationship is here. Looks like a top opening parabola married to a bottom opening parabola. Okay. Looks like, I don't know. It looks to me like we're saying it's top opening, or no, side opening. Yeah, they linearized it. They said it was side opening. This group here said it was direct model right off the bat. Direct model, direct model, direct model, direct model. This one, they said, again, it was a side opening model. Direct model, direct model, direct model, direct model, direct model, direct model, direct model. Okay, it looks to me that most people are saying it's a direct model. So let's see if I can just find one that has direct model here. I think we're going to go ahead and go with this one. I want you to notice that some groups were saying that the momentum is along the y-axis and the impulse is along the x-axis. First of all, I need to stop right here and define something. I did this in the notes, but I want to go ahead and say it again. Impulse is, it's kind of the area, it's equal to the area bounded by a force time graph. So I think I want to review a little bit before I go much further. So back with the energy unit, think of the springs again. So you remember how we plotted the force of a spring versus the stretch, X. And it kind of looked like this. We defined the area underneath this graph. We defined this area as the energy. Well, this graph that we're talking about for impulse is a little bit different. It is a force graph, but it's not force versus stretch, it's force versus time. So it doesn't have to be a spring force, it could be any force. So now let's imagine that we change it from X to time. So you're looking at, let's say you're punching a pillow. You're just getting tired of being cooped up in the house, you're punching this pillow. Imagine as your fist is moving, at first, you know, there's a certain contact force, and then probably as you keep on pushing, it gets a bigger force, right? And eventually you're going to extend all the way through, and you can't really push as much, so that force kind of goes back down. So first of all, let me get rid of this. The graph probably wouldn't look like this. The graph would probably look different. It'd probably look more like maybe something like this. This area is called the impulse. We're just defining it to be that way. So the area of this force time graph is impulse. Now the graph doesn't have to look like that. In the lab that you were doing, this was an astronaut, if I remember correctly, and they had some kind of jetpack, and you turned that jetpack on and it shot them through these two photo gates for you. And in that case, that force was a constant force. And so in order to figure out the impulse here, that would just simply be force times time. Totally different than the one we had a second ago. If I wanted to find the impulse here, again, the area of this would be 1/2 the base times the height. Or if you had some totally different graph, let's say a graph that looks like, let's see if I could draw it anyway. Let's see. I don't know, let's say it kind of looks like, I don't know, we're flattening a curve, too much television. So something like this. I mean, if I want to find the impulse in this case, again, I'm finding the area, but that was a little bit more difficult. I would have to use some calculus to figure that out. I'd have to do some integration. But for a force time graph, we're calling that impulse, okay? So it's not exactly it's not the same thing as energy, okay? So sometimes students kind of get that confused a little bit. Okay, so having said that, let's look at everybody's model here. So this one here was linear. Oh, that's right, we did this one. Most people said it was a linear relationship. Okay, so, oh, I remember what I was gonna say. Some people had the momentum along the vertical axis, like this group here. And then I thought I saw some other groups that had impulse. Yeah, notice this group here has impulse along the vertical axis. So I want you to really think about, we're trying to figure out which one's the dependent variable. It ends up giving us a linear relationship either, a direct relationship either way, but we really need to think about which one's the dependent variable. Think about, we had the astronaut, we turned on the jetpack. The momentum is changing depending upon how long the force is turned on. So I don't think the impulse, which is force times time, I don't think that depends upon the change in momentum, which is like mass times velocity. The longer you have that jetpack turned on, the more the velocity changes, the more the momentum changes. So I don't think we have our axes correctly in this graph. I think it's going to be more something like, where was I? I lost it. It's going to be more like this, where the momentum, the change in momentum is along the vertical axis. That's the next thing I want to talk about. This momentum of the astronaut, that was the final momentum, right? They went between these two photo gates. So you found the mass times the final velocity. But what was the initial momentum of the astronaut? when they were just sitting there before you turned it on? Anybody say something?
0.
0. So the truth is, this is the change in momentum. So I'm going to see if I can kind of draw a little triangle here. So it's really the change in momentum. So I think what I'm going to, I suppose it's fine to say that it's MVF. That's true. It's totally true. But I want you to understand it's really the change in momentum. So it looks like they're saying it's a direct relationship. The slope is 0.85. I think I want to go look at all the groups that have a linear and figure out what the slope was. They didn't have linear. Here they had the slope of 1, 0.85, slope of 0.84, slope of 1, it looks like about, slope of 1.02. No equation. Wait, no, they have in the bottom, sorry. They're saying side opening. So it looks like they have a slope of 1, slope of 1, slope of 1, slope of 1, slope of 1. Looks like they're saying slope of 1, slope of 1, slope of 1.4, slope of 1, and it looks like a slope of 1. So I think we're going to say the consensus is it's a slope of 1, okay? So the consensus model is going to be the following. First of all, I'm going to write it out in words so that we understand conceptually what it means. What we're saying here is the change in momentum is equal to the impulse. In other words, the longer you have a force being exerted, because it's really kind of the area of this graph over here, the longer you have a force being exerted, the greater the change in momentum, mass times velocity. I think it makes sense. Anybody who's in sports, you probably had your coach tell you, hey, make sure you have good follow through, whether it's golf or it's tennis or whatever, or basketball, right? Have good follow through. Why is that? Well, what you're doing when you follow through is you have a longer time of contact, which means you're exerting that force more. Or even with tennis, right? If you're serving, you want to have a good follow through, so you have a contact for a longer duration of time that you're applying that force, which means you have a bigger change in momentum. And so the final velocity is bigger, which means it goes further. Or if you're in tennis, it's faster, harder to return. So that's kind of the connection. Now I want to go ahead and put this as an equation form. So change in momentum, let's see if I can, well, first of all, I'll just put the P. I'll come back and put the delta in a second. So P equals, now the symbol we usually use for impulse is the letter J. Not always, especially in the AP test, you'll see a J. So the impulse, I'm going to use a J here. So let's see if I can draw a triangle again. Maybe I'll just steal this triangle here. Okay. So we have a change of momentum is equal to the impulse. So realize that momentum is a vector quantity. We just talked about that. Oops. That means that the impulse is also a vector quantity, so it has direction. Okay, so there's the equation. That's what the impulse does. The impulse causes a change in momentum. That equation is a nice generic equation that would help you pretty much any time. So for instance, if your graph kind of looked like this right here, but if I go back to what you did in lab, yours was a constant force. It didn't change, it wasn't variable. And so really the equation becomes even easier in your situation. It was kind of like the change in momentum, MVF, minus MVI, the initial velocity was 0, so that dropped out, equals, well, it was a constant force. So F, if you're looking at this over here, how to find the area? Well, it's constant force times the time interval. So times delta T, I'm just going to put T, okay? Now, I want you to understand that this equation is not true always, because you would have to have a constant force. So for instance, if I'm going to go back to, what if I had a graph that kind of looked like this, like you're punching a pillow or something? So your graph would probably look like this. Well, in this case, it would be 1/2 ft, because how do you find the area of a triangle? It's 1/2 the base times the height, so 1/2 f times t. And if it looked like the original graph, I'd have to integrate to figure out what the area is. So I just want to make sure that you understand that. The other thing I want you to understand is that the impulse is not equal to the final momentum. It's not equal to the final momentum. It's also not equal to the initial momentum. It's equal to the change in momentum. So some students, the reason I'm stressing that is sometimes students get that confused. They think, oh, impulse equals momentum. No, it equals change in momentum. Okay. So any questions on that? Okay, so let me go back to the this page here. So all we're going to do today, which we're almost done here, all we're going to do today is just simply whiteboard the graphical and mathematical models so that you know those, okay? There are other parts to this lab response. You do not need to have those done, okay? So it's just like in class, we're going to whiteboard those, and only after we have it whiteboarded so that we feel like everybody knows what they're doing, they've invested some time in the models, then the next day you're going to turn it in. So that's when you need to make sure you have it completed. I forgot to mention I needed to talk a little bit about the AP test, and you probably know this already. You probably got the email from the principal that talked about the last day of AP testing. Hey, there's an upside to this this pandemic thing. Class is actually officially over for us the day of the test. Well, the day of the test for you guys is actually the very first day of AP testing, which is Monday, May the 11th. Well, that's kind of during the test. I mean, that's the test day, and I don't want you to contribute to your anxiety. I definitely don't want you to be studying that last day. It's too late at that point. So for us, the last day is actually going to be the previous Friday. So that's kind of exciting. So mark that on your calendar. Again, as far as the test, I believe there's 2 problems. The last thing I saw, 2 problems. I think one's 15 points. The other one, I can't remember if it's 10 points. It's going to be over units 1 through 5 according to the College Board. So for instance, the last test we just took over universal gravitation and uniform circular motion, sorry, that's not going to be on there because I kind of do things out of order. It's also, that's unit 6 according to the College Board. Unit 7 won't be on there. That's something we've also been working on, the oscillations, like with the pendulum and the spring and stuff, where you have t squared equals 4 pi squared, all that stuff. So that won't be on there. This unit, momentum, will be on there. I'm not too concerned about this unit. It's kind of an easy unit. True, it is vectors. That's one thing you have to be worried about. But, so were kinematics. Kinematics were vectors too. And if you think about kinematics being vectors and dynamics with the forces, force diagrams, definitely kinematics was easier than forces, right? I mean, you do have to worry about negative symbol, like if you have something to shoot up in the air, but the acceleration's downward, you have to remember to make something negative. Same kind of thing with momentum. I actually think momentum's a little bit easier than kinematics even, but you have to be aware that if you have things exploding away from one another, or if you have something that's bouncing, and it changes direction, you need to put a negative in your calculation. But if you don't forget that, you're good to go in this section. It's pretty easy. Anyway, the point is, I think we're going to get through this unit, no problem. The only other thing to tell you is that I don't think we're going to be even able to talk about Unit 5, which is the one I'm kind of worried about with rotational stuff. I've opened up the AP Classroom where you can start looking at that stuff. But I will tell you this, the very first year I started AP Mechanics, I probably should give you a little bit of background. Before we started AP Mechanics, there was honors physics, kind of like there's honors chemistry. Well, here's the issue. In honors physics, we pretty much covered everything, except for, there was just a couple things compared to AP, sorry. In honors physics, we pretty much covered everything that was on the AP Mechanics, except for just a couple things. And so I kind of felt like that maybe I was cheating those students out of, an opportunity to get some college credit. And so some kids came to me and said, hey, why don't we do this? And so I thought, just for those motivated students that, are willing to study a little bit on their own, I wanted to give them that opportunity. That's why we started it. So that first year that we actually offered AP Mechanics, I didn't even get to the rotational dynamics unit, the one that we're not going to probably get to either. On top of that, I didn't even warn them about it. I didn't say, hey, you need to study that on your own, because I didn't want them to be anxious going into the test. Now, having said that, there were a few students that came to me that were, the top students that were really concerned. They wanted to get a 5. And I told them, hey, you should study some of this stuff on your own if you want to, make sure you get a 5. And I was a student who, she was just over the top. She's now a doctor, went to Vanderbilt. She got a 5 that first year. Now, I didn't have a whole lot of 5s, but I did have 4s and 3s. Those students kind of studied on their own. And I think if I would have warned them and said, hey, maybe you should start looking at some of this stuff on your own, maybe come to me, talk to me at office hours or whatever, I think I probably would have had more 4s and 5s. So I guess the point I'm telling you all this for is that if you want a 4 or 5, and you're willing to put a little bit of extra work on your own, you can get a 4 or 5. Okay. So anyway, any questions? Okay, the last thing you need to do is you need to take this attendance quiz. And so I need to give you the code to access it. So this should be a really simple thing. It's just based upon what we just whiteboarded. So if you were paying attention, it shouldn't be any problem. So let me go ahead and give you that code. And you can take it as many times as you want, but I want you to get 100%, but it shouldn't be tough at all. It's based upon what we just whiteboarded. And the code is right here. So if you can copy down that code, and it closes at midnight tonight. Okay, so any questions? Everybody have that code? It's 16, lowercase d, lowercase f, 676, lowercase e, uppercase w. Okay, don't go yet because I want to make sure kind of attendance here. Can I stop sharing? Everybody have that code? Okay, I'm going to assume that you have it. So any questions? Okay, our next meeting is next Tuesday. It's the same time, same place, same bat channel, and it's another Zoom meeting where we're going to finish doing the whiteboarding of this. Okay, all right, see you later.
I had one question, Mr. Lefesti.
Yes.
It's the same question as Krishna. How do the FRQs work on the AP test? I don't remember them talking about that. I thought it was just multiple choice, but
Are you asking me how are you going to submit it and everything?
yeah, like are they still doing it?
Yeah.
I didn't know if you knew that.
Well, I'm just going to tell you what I know. Okay, and so you need to understand this is really kind of weird. It's not that I'm concerned. I do have some concerns. It's not concerns about your ability or anything. I have some concerns about the system. I'm worried about the system crashing when you guys are doing it. I'm worried about what you're mentioning. How are you going to put in your answer? And I mean, it was hard enough when we did stuff on Canvas, right, on the last test. That's why I made it so long. I gave you guys like, I don't know, like an hour and 20 minutes because I was worried that somebody would run out of time typing in their answer. So I don't know. This is one of the things I heard that you can do, and this is probably what I would do. It says, what I saw somewhere is that you can actually upload picture of your work. I personally would I think you have to go to a site to look at so everything's on the computer. So the problem will be on the computer, but I personally think if it's possible, because they're not sharing a whole lot of information, but what I've heard is that you could take pictures of your work and then upload the picture. I think that's what I would do. I'd do the work on a piece of paper and then upload a picture, take a picture of it with your cell phone or something. I think that's what I'd do, because I'm a little bit concerned about you guys having enough time, because I think it's only 45 minutes. And yeah, it's not multiple choice. It's just going to be free response.
Well, it's 45 minutes. Then you get like a 5-minute uploading period at the end is what I get from like all the other classes is what I've heard. So I don't know how, like what happens if you don't get it in during that 5-minute uploading period? Are you just getting a 0?
I don't know. That's kind of what I'm kind of worried about, especially, I mean, at the very beginning of the year, I didn't use the AP Classroom, but I imagine some of you did in some of your other classes. My understanding is there was all kinds of problems where I'm just worried about the network. I mean, you hear about people now, they're trying to file for unemployment and the system crashes. What happened? It makes me a little bit worried. And so I don't know. But here's the thing. Don't worry on your end because you know what? The College Board they're saying that this is going to be doable. Well, you know what? We're going to hold them accountable. It better be doable. It's not your fault if something crashes. So don't worry about that. That's more of me worrying, and they need to worry, not you worry. Okay.
And most schools already said, colleges, that they're not going to require the test this year. Like a lot of them are saying that, and just automatically make it pass.
Oh, really? I didn't hear that. Okay.
Yeah, there's a couple of them that have said that. I think more and more are following on that trend.
Huh. Well, yeah, because I mean, they are telling us about the test. They're saying it's going to be 2 problems. They say it's going to be free response. But I have a lot of questions, and the same questions you have, and I have posted them. I said I'm worried about it crashing, and I'm worried about this, and I'm worried about colleges accepting it. Are they going to put a little star by it of So I don't know. I mean, I don't think you should worry about it. I think just do what you always do, and they are the ones that held accountable. You aren't, so I wouldn't worry about it too much. Okay. But I would really like them, I haven't heard this, maybe somebody else has, I would like them to do like a practice test. That way all of you can get on whatever their system is and actually try it. And, that way you understand how to upload and how to do this. That would make me feel a little bit more confident. I don't know, does anybody know if they're doing that?
I do not.
Yeah, okay. So I wouldn't worry about it. I'm posting questions, and when the time gets closer, hopefully we'll have more answers.
Okay.
I thought I heard we would have to sign in 30 minutes before the test to try making sure everything can be you understand how to submit everything and stuff like that.
Okay, so it's right before the test that they're going to have you kind of
That's
practice.
what I heard, but I don't know.
Yeah, I heard that same thing. I think she's right. You have to be there 30 minutes before so you can check everything out, make sure it works.
I will check into that too then a little bit. Any other questions?
Wait, so are the FRQs going to be formatted like the calculus ones, or are they just give
What do
us
you
a
mean?
problem?
What do you mean formatted?
I don't know, they're going to have an A, B, and C, and then you have to go through it, I guess.
I don't know for sure, but my guess is that it will have you'll be given a question and there'll be part A, part B, part C, but I don't know exactly how you're putting your answer on there exactly.
Okay.
Yeah, sorry. I'll see if I can dig and find out some more information on that.
Okay, thanks.
Oh, probably I should say one more thing. I forgot to say this. The internet homework, please don't forget about that. Again, you only have to do 6 problems. There's 14 there. You get to pick and choose. Even though tomorrow's Good Friday, I'm going to still be available. If you'd like to ask questions or something, you can send me an email. Maybe we could Zoom meeting one-on-one or something like that. So.
Okay, awesome. Thank you.
All right. Yep. All right. Well, thank you for attending, and see you later. Bye. Okay, so wait, Luke's here still. Luke, did you have a question real quick? Okay, I'm gonna kick out Luke here. All right, Dan, Adam. Yeah. So I tried to, I don't know if you heard me there in the beginning. What I'm trying to do is I'm just trying to make sure everybody's participating. I'm sure that you guys were participating. And you were just kind of talking behind the scenes, but I just need to know going further, from now on.
I think it was just a miscommunication on our part, because we both, the 3 of us, me, Dan, and Brian, all FaceTimed and shared our data with each other, and then got a consensus and then drew out the things. I guess we just miscommunicated on who was writing what down and if we were all sharing together or not.
Okay.
Because we also like FaceTime for all the questions and stuff, and we were just
Okay.
talking the whole time. But I guess we just weren't on the same page on if one person was writing it down and sharing, or if we all were.
Okay, it totally makes sense to me. We're all learning this. So I don't have a problem with that. I mean, I totally believe that you guys were doing that. It's just I need some way of verifying. So maybe from now on, when we do whiteboardings of labs and stuff going in the future, maybe you just all kind of collaborating on one whiteboard. Like, okay, you do the math model, I'll do this part of the graph, you do that part of the graph, or maybe even just include a chat there on the side of, this is what I did, here's my data, this is my data, yeah, we all agree, you know, that kind of stuff. That way I can see that everybody's participating.
All right,
Okay,
sounds good. I
sounds
think we just miscommunicated that.
Well, you know, we're all just kind of learning this and doing the best we
Yeah.
can.
Yeah.
All right. Okay, thanks.
Yep,
Bye.
no problem. Bye.
Yep, bye.